tightly to your seat when a roller coaster rushes into a giant loop. And yet, strangely, sometimes it feels like your body's floating. Your stomach tightens and you suddenly feel light. So where does this feeling of weightlessness come from? Today, let's explore it through physics. So in physics, the mass we feel, what we usually call weight, isn't actually gravity itself. It's the normal force, the upward support force from the ground or sea that keeps us from falling. And this is the real mechanical signal your body senses. So even though gravity is always pulling you down, if that support force disappears, you will feel weightlessness. Let's take a closer look at how a roller coaster creates this feeling. Imagine a roller coaster is going through a vertical loop at a certain speed. When the car reaches the very top of the loop, you're right at the highest point. And at that point, your body is under two forces. Gravity, mg, pulling you down, and the normal force from the seat, which also points downward here, because the seat is pushing you along the loop to maintain circular motion. These two forces together make up the net centripetal force Fc required to keep you moving in a circle. And the equation is Fc equals to mv squared over r. So obviously, the normal force is equal to the centripetal force minus mg, which is mv squared over r minus mg. And keep m outside, we get that Fn is equal to m times v squared over r minus g.
Now let's look at three scenarios. First, if the roller coaster is moving fast enough, then v squared over r is greater than g, which means the normal force is positive. That's when you feel pressed hard into your seat. It's pushing you down and you feel heavy. Second, if the speed drops just enough so that gravity alone provides the necessary centripetal force, then the seat no longer needs to push you. That's when the normal force becomes zero. At this point, you're in a state of complete weightlessness. To confirm this, we conducted a real-life experiment. We rode a roller coaster with the accelerometer and recorded the net vertical acceleration at the top of the loop. At the moment we feel weightless, the graph shows that the centripetal acceleration, which equals to v squared over r, is about 9.41 meters per square second, which is exactly the gravitational acceleration. That confirms it. When net acceleration equals g, then n equals 0. At the moment, we feel weightless. Third, what happens if the speed gets too low? If v squared over r is less than g, then the normal force becomes negative, which means the seat can't hold you in. That's when you lose contact and risk flying off the track. That's why roller coaster speeds are carefully calculated. But roller coasters aren't the only place where you can feel weightless. Another common example? Elevators. Let's do a quick force breakdown for a descending elevator.
Gravitational force, downward. The normal force that supports you, upwards. Since the elevator is accelerating downwards, the direction of acceleration is downward. According to Newton's second law, the resultant force should be downward. And that gives us the normal force equals to m times the result of g minus a. When a equals to g, the normal force becomes 0. That's total weightlessness, exactly like on the top of the roller coaster. This is how drop towers work. We test this too. Using the VFox app, we measure vertical acceleration during a drop. At the moment we feel weightless, the net acceleration again came close to the gravitational acceleration. So just like before, the data matter theory, when the normal force equals to 0, the net acceleration equals to the gravitational acceleration, g. So in the end, being weightless doesn't mean you have no weight. It just means for a brief moment, the support force is gone, and that's when you float.